I'm back with some more materials questions. So let's see how many we get in the next sort of 20 minutes or so. On the axes below, sketch a stress against strain graph for a typical ductile material. Well, it's open to debate what typical means, but ductile material. So we want to start off with our straight line. This is our region of Hooke's law applying. After this, I mean, you've got various things you can draw on, but we need to have something for ductile material where you're getting a big increase in strain for little change in stress, or even a reduction in stress. These can take various forms. You get graphs that look like that. You get other ones. If I start off with a different straight line region where you have the yield points, so it might come over, sort of something like this. You can get variations in the ductile region in this area of plastic deformation. But the main thing is we need to have this big change in the strain for a small change in stress outside of our linear region. So any of these sort of ones are going to be fine for ductile materials. Circle from the list below a material that's ductile. All right, so some of the words seem to have disappeared here. I'll just have a quick look. All right, so this one is copper. Then that is ceramic, probably could work, and that must be glass. Yeah, so we got those. Right, so we're looking for materials that you can, under the right conditions, sort of play around with as if they're plasticine. You can get these big changes in dimensions. They become malleable and pliable. We can turn them into different shapes. Now you can't do that with jelly. Once jelly's set. You can't just start remolding it into something else unless you're going to melt it all down again. So we're not going to have that. Ceramic and glass, these are brittle materials that just snap. Copper, we know we can, manipulate that around. You can hammer it into shapes. You can turn it into wires. So yeah, copper is the one to go for. Now we've got define the ultimate tensile strength of a material. So this is our maximum stress. So the sort of most force you can apply per unit area, the maximum stress that can be applied before breaking that material. So that's just a definition on that one. Similarly, we've got state Hooke's law. That's our extension is proportional to the force applied, but that has to be within the elastic limit. So you need to make sure that you've got that mentioned as well. Right, so yeah, quite a few little bits there for starters. Now we're on to the bulk of the calculations here. We've got a mechanism for firing a table tennis ball into the air, which is just a spring which pings it upwards. Spring has a force constant of 75 newtons per meter. Spring is compressed by a certain amount. Calculate the force exerted by the compressed spring on the ball immediately after the spring is released. Assume both the spring and the platform have negligible mass. All right, interesting. So they've described it as negligible mass here. I mean, this is getting back to Newton's second law. What is the force actually doing? The force is going into accelerating things with mass. You don't need force to accelerate the things that don't have mass. When we're in our world of classical mechanics here, this is what the force is doing. It's moving mass around. So we're just looking at what's happening to the table tennis ball. So we can use our F equals Kx. The K is 75. The X is 0.085. We're still working to two significant figures here, putting all that in. So we've got 6.375, so 6.4 newtons to two significant figures. The ball, the mass of the ball is not a lot. It's 2.5 times 10 to the minus 3. Calculate the initial acceleration of the ball. Okay, so we're now doing our F equals ma on this. F equals ma. We've got the force, which was 6.375. Divide that by the mass, which is 2.5 times 10 to the minus 3. This is going to be quite the acceleration. So 6.375 divided by 2.5 is 2.55, and that'll be multiplied by 10 to the 3. So 2550. Which is 2,600 to two significant figures. Meters per second squared, don't forget the units. Calculate the maximum height that could be gained by the ball. Assume all the elastic potential energy of the spring is converted into gravitational potential energy of the ball. So we've got mgh is equal to a half kx squared, and we want to get h. So h is going to be equal to k is 75. X was the 0.085, and we need to square that, and then we need to divide by 2, g multiplied by m, 2.5 times 10 to the minus 3. Okay, so we put all of that in, and what have we got? We've got 75 times 0.85 squared. We need to divide by 2, divide by 2.5, divide by 9.81. So we've not got a lot. We need to multiply that by 1,000. So that's 11.047. So 11 meters sticking to our two significant figures. So yeah, once again, the calculation's fairly straightforward. Quite a lot of stuff on terminology and things to begin with. Right, next we've got a sample of wire that's been tested in the lab. We've got a graph of force against extension for that wire. Right, explain how the graph shows that the wire obeys Hooke's law. So that's just that our force is proportional to the extension. Then we need to state what the gradient of the graph represents, which is the force constant of the wire. So that's fine. Two nice starters there. Initial length of the wire is 1.6 meters. They've given us the radius. Use the graph and that information to determine Young's modulus. Okay, so Young's modulus is the force times the length over the area times the extension. We've got force divided by extension we can pull off of the graph. I mean, they've drawn this line straight as an arrow, so we can take any pair of points and just take the ratio, because that'll be the same as the gradient because it's going through the origin. This is bit like what we were discussing on the previous video about Young's modulus. We take the gradients of these when we've got experimental data and we're doing a best fit, because it gives us a nice averaging to get our sort of, a best fit for Young's modulus or the force constant. But when they've drawn it as a dead straight line, we can just take a point that's easy to read off of the axes here. So we've got 100 over 4 times 10 to the minus 3. And we can use that as our f over x. So that will be a quarter of 10 to the 5 for our f over x. We then need to multiply by L, which is 1.6, and then divide by a squared. So we've got a 2.8 squared. We'll have to have a pi in there as well to get the circular area, and then we're going to have a times 10 to the 8. So we've got a 10 to the 13, and then we've got all these bits and bobs kicking around. So we can get rid of that quarter and make that a 0.4. So all in all, we've got 4 divided by 2.8 squared times pi times 10 to the 12. So type all of this in. 4 divided by 2.8 squared is that, divided by pi is that. So 1.62 times 10 to the 11. We're still only operating at two significant figures, despite what I've given us here with a 1.60. So I'm going to leave that as 1.6 times 10 to the 11 pascals to two significant figures. So that's Young's modulus. Then we've got the test is repeated for another wire made of the same material. It's got the same Young's modulus, different, same length, half the diameter. Right, so we've got that is unchanged, E is unchanged, L is unchanged. We've got that A is now a quarter because the diameter is halved. So if these two, if L and Young's modulus are unchanged, that means our F over X is going to have to be a quarter of the value as well. Therefore, F over X must be 1/4 of the original value, which means, and that is the gradient. So yeah, explain how the force against extension graph will differ. Therefore, the gradient is 1/4 of the original gradient. Right, so that's all fine. It's very dangerous if the wire under stress suddenly breaks. Yep. The elastic potential energy of the strain wire is converted to kinetic energy. Show that the whiplash speed V of the wire is directly proportional to the extension of the wire. Right, so we've got conservation of energy. I mean, they've told us that's going on here. We've got a half kx squared. That is our EPE, and that is going to go to a half mv squared. I mean, we can immediately see that they're going to be proportional because we've got the two things squared. We can get rid of those. And let's make V the subject. So V equals the square root of K over M multiplied by X. So i.e. V is proportional to X. So that's quite a straightforward one to wrap up on. It's just making sure, well, essentially you can pull out the EPE equation from the formula booklet or from memory or from first principles. You know, maybe you're going to want to go about doing it that way. I mean, it is just, yeah, if you recollect with this is just force times distance. So we've taken F equals Kx. So our average force is going to be a half of Kx, because we're starting from 0 and we're going up to Kx at the end. So that's our average force, our F bar. So you multiply that by the distance it is moved through and you get a half Kx squared. So it's quite easy to go back to our first principles and just say work done is the average force multiplied by the distance moved in the direction of the force. And then lo and behold, you've got your EPE equation. Right, now we've got some duplication coming in here. So state Hooke's law, we've done this loads of times. Extension is proportional to force applied, but that has to be within the elastic limit. When we've got a force extension graph for a spring, describe how this graph can be used to determine the force constant and the work done. So the force constant is the gradient and the work done is the area under the curve. Right, so that's nice quick starters. Then two identical springs connected together in series. Force constant of each spring is K. Three ends of the springs are pulled apart as shown, right? So we're pulling them apart. Explain why the force constant of the combination is K over 2. Right, yeah, sometimes people know what they want to do with this, but have trouble sometimes explaining what's going on. So the force constant is the force divided by the extension. So for two springs, for the two springs setup, we can say that the new force constant, let's call that K with a subscript 2, we've got the same F, but we've got a new now extension. So we call that the extension X subscript 2. But then we can say that X subscript 2 is equal to 2X, which means we're going to there get F over 2 times X, which is equal to K divided by 2. So as soon as you put in these new ones here, these new subscript K, K2 and an X2, it means we can rewrite everything in terms of the original force constant, and then it just drops out in a simple description. I find that a lot of people just get themselves into a mess and start going around in circles when they try to, describe this in sentences. It's one that I think is just so much easier done if you keep in a little bit of algebra like this and put in these two new variables, K2 and X2. Right, last part of the question. Define Young modulus of a material, state the condition when it applies. Okay, Young modulus is stress divided by strain, and that is within the region of Hooke's law, or you could say within the elastic limit, or when there's no plastic deformation. These are all the same way, different ways of saying the same thing. Now we've got some calculations. They've given us L, they've given us A, they've given us F, and they've given us strain as well. Okay, so they've given us the strain. So all of those things are in the question. Using all of these, we need to calculate the stress. So stress is equal to F over A. They've given us F as 4.2. A is 0.2 millimeters squared. So we've got a 0.2 millimeters squared. So that means times 10 to the 6 when we put it into meters, when we're dividing by that area. So that is going to be 21 when we do that divisor, as in 2.1 multiplied by 10. So we've got 2.1 times 10 to the 7 pascals is what we've got for our stress. What is Young's modulus then? So Young's modulus, that's stress over strain. So we've just worked out the stress, 2.1 times 10 to the 7, and they've given us the strain, interestingly, as 1.5 times 10 to the minus 2. So we've got a 10 to the 9 there. 2.1 divided by 1.5, so that's the same as multiplying by 2/3, so that'd be a 1.4 times 10 to the 9 pascals. It's got the same unit, isn't it, because strain is dimensionless. And then the elastic potential energy stored in the string. So we've got EPE is a half kx squared. So where extension, so we now need to look at our strain here, because strain is extension divided by length. So that strain multiplied by length is going to be extension. So we got a half times k. Have they given us k? I'm not sure we've even got. Have we got k? No, they haven't. Oh, interesting. So, but k is force over extension. So, right, let's put all of that in then. So we got force over extension multiplied by extension squared. So we didn't really need to put in, I should have used the other version of the elastic potential energy. This usually seems to be the go-to one with a force constant in, but it's actually a half Fx is another way of doing it as well. So it's your average force multiplied by the extension. And the extension is the strain times the length. So a half times FL times the strain. All right, get there eventually. I've taken much longer on that than I should have done. Right, I'm going to have to write the numbers somewhere else on the screen and then just stick the answer down the bottom. So we got a half times 4.2 times the length is 0.7 multiplied by the strain, which is 0.015. So we need to stick all of that in and see what we get. So 2.1 times 0.7 times 0.015, which is 0.022. So 2.2 times 10 to the minus 2 joules. So not very much, but you wouldn't expect there to be very much energy in there. So yeah, kind of went a little bit around the houses there, but that shows the thing of don't get too fixated on one description of elastic potential energy there. I jumped in too quickly doing this half kx squared. So keep the other one in mind, the half fx. I know it didn't exactly cost a load of time, but you've got two descriptions there of the same thing. We just seem to use the other one more often, so it can be easy to get just stuck in your ways.